Hi students, welcome to my lectures on chemical engineering thermodynamics. Please follow my lectures from the beginning as every lecture is connected. In today's lecture, we are going to continue the topic of partial molar properties. In the last class, we have discussed about how to find out the enthalpy of any component in a mixture. In today's class, we are going to measure now entropy, because enthalpy and entropy combine to form Gibbs energy. So in the last class we have learned about the finding out the enthalpy of any component in a mixture. In today's class we are going to find out enthalpy of any component, entropy of any component in a mixture. Let us go back to the board. Here the Gibbs theorem says that property of any component in a mixture at a given temperature and pressure will be equal to the pure property of the compound at temperature T but at a pressure Pi, which is called partial pressure. That means, imagine I am finding out the entropy of A in a mixture and B in a mixture. A and B constitute one mixture. I need to find out what is the entropy, partial entropy of A in this mixture and partial entropy of B in the mixture. Okay, so let us apply the Gibbs phase rule to find out the entropy, partial entropy of A in this mixture. So here it goes. The property now we are measuring is the entropy. So entropy of ith component in the mixture at a given temperature and pressure will be equal to pure component entropy at temperature T and partial pressure Pi. Okay. The another definition of finding out the entropy of any component in the mixture at the given temperature and pressure is equal to pure entropy at a given temperature and pressure minus R ln Yi. So according to this formula, you have to find out the pure entropy and you have to add or add something. If minus, it will automatically become plus, because ln of fraction anyway it will become a negative. Negative into negative, it will become positive. Okay, that means for you to find out the entropy of any component in a mixture, you should know pure entropy plus R ln Yi. This minus R ln Yi, that means you have to add something here, because entropy is always increases in a mixed state. Okay, this parameter will help us to find out the increase in entropy because in a mixed condition. So how this formula has come from this formula? The detailed derivation is given. If you follow the, if you know the thermodynamics well, then entropy of the ideal gas, change in entropy of the ideal gas dSig is nothing but Cpiig by T into dt minus R by P into dP. So from this formula you can calculate the change in entropy. All the derivations, concepts we learn in chemical engineering thermodynamics by keeping temperature as a constant, because if you change the temperature, the value of every property is going to change drastically. So in all the derivations, normally we keep temperature is constant. If the temperature is constant, the change in temperature dt equal to 0. That means this first term value will be equal to 0. Then the change in entropy is nothing but minus R by P into dP. Let us integrate this term from what conditions? From P, that means total pressure P to Pi, because here we are interested in P to Pi. So let us integrate the entropy from initial state, which is at temperature T and P, to final state T to Pi. P is the total pressure, Pi is the partial pressure. Example, somewhat different pressure. Okay, that means at these conditions, entropy at T and P, the pressure is P. Entropy at T and Pi, the pressure is Pi. Around this variables, you have to integrate between these two limits, then you get entropy at T and Pi is equal to minus entropy at T and P equal to R ln P by Pi, because if the minus goes here, then automatically the value will be inverted. So R ln P by Pi. Therefore entropy at T and Pi, which is our objective, okay, don't worry, we'll come slightly towards. Entropy at T and Pi will be equal to entropy at P plus R ln P by Pi, okay, because somehow you get the value of T comma Pi. Here you get entropy at T and Pi, you are going to get the value, okay. If you see for ideal gas, okay, the partial pressure is nothing but the mole fraction into total pressure. Simply in place of partial pressure, substitute the mole fraction into total pressure, and this P and the bottom P will get cancels out. You get 1 by Yi, okay. If Yi comes to the numerator, the minus will go here because inverse of the logarithm, okay, -1 inverted, okay. Then plus RT ln 1 by Yi. If Yi comes at the top, -1 appears here, the -1 comes to the front. Then the entropy at T and Pi, partial entropy, which is equal to the pure entropy at T and P minus R ln Yi. This is how this equation has come by following this derivation. What is our objective? Okay. Now you know entropy of any component in the mixture can be estimated using this expression. The partial entropy of A is denoted as S bar A Ig. Partial entropy of B is represented by S bar B Ig. Entropy of this total mixture is denoted by Sig. Ig is representing ideal gas conditions. Let us find out this expression. Let us follow this formula. If I wanted to find out the partial entropy of A, I have to apply this formula. What is the partial entropy of A? Is nothing but pure entropy of A at T and P minus R ln Ya. What is the partial entropy of B? Okay, what is the partial entropy of B in this mixture? Is nothing but total entropy, pure entropy of B minus R ln Yb. So if you see the diagrammatically or pictorially, I am describing it. What we are trying to find out, entropy of this partial entropy of A in the mixture. Okay, this is representing the pure entropy. Pure entropy means only A is present, and you have to add or subtract something. Okay, in fact it is addition, not subtraction. You have to add something. What is this adding? If entropy, if you mix two things, entropy always increases. That is called entropy of mixing. The term R ln Yi representing the mixing of A and B. That means entropy, partial entropy of A is nothing but pure entropy of A plus mixing of A and B in this container. So that is why diagrammatically it is representing. Similarly, the partial entropy of B in the mixture is nothing but pure entropy of B plus mixing of A and B. So this is how you can able to relate the story. So partial entropy, molar entropy, that means S bar A, it's a entropy of A in the mixture, S bar B, partial entropy of B in the mixture, is always higher than the pure molar entropy. That means this is a pure entropy of B, this is a partial entropy of B. So always the partial entropy is higher than the pure entropy because of this mixing of A and B in the container. So if you follow the example, you will understand it much better conditions. So wherever you have to find the value of partial entropy of A in the mixture, you have to follow this formula. So let us apply one example so you can learn much better. Find three things. One is partial entropy of A in the mixture, partial entropy of B in the mixture, and total entropy of A plus B. Okay, these are three things. At what conditions? The conditions in this container is given as 200 degrees centigrade and pressure equal to 1 bar. So you have to find out these three at defined temperature and pressure. Let us apply. Given Pure entropy value of A is given. How much? At 200 degrees centigrade and 1 bar, pure entropy of A is 30 joule per mole Kelvin. At 200 degrees centigrade and 1 bar, pure entropy of B is given 40 joule per mole Kelvin. Mole fraction of A and B are given. That means Ya, this is Ya is given, Yb is given. Ya is equal to 0.4, Yb equal to 0.6. Now you have everything is given. Apply the formula here. Partial entropy of A at 201 bar is nothing but pure entropy of A minus R ln 0.4, which is 37. Okay. And how much is the pure entropy? If it has only pure entropy value is 30. When it is mixing with B, what happens? The total entropy from 30, it has increased to 37.618. Similarly, if you follow the partial entropy of B in the mixture at 200 degrees centigrade and 1 bar is equal to pure entropy of B as 201 minus R ln 0.6. What is the value? 44.2. What is the pure entropy of B? 40. When it is mixing with A, what happens to the entropy? Entropy of B is increasing in this mixture. At what to what value? From 40 to 44.247 joule per mole Kelvin. So, as you can observe, mixing of the two components will rise the entropy. Third condition we have to find out total entropy of the mixture. We use summability relationship. From the summability relationship, the total entropy of this mixture is summation of the partial entropies. So what is, if I expand the sigma yi s bar I ig is nothing but ya s bar a ig plus yb s bar b ig. S bar a I know, s bar b I know ya, I know yb. So if I calculate, the total entropy of this mixture is around 41.595 joule per mole Kelvin. Okay, so this is how in the last class we have found the partial enthalpies of A and B in the mixture. Today we have found partial entropies of A and B in the mixture. In the next class we connect these two formulas. Gibbs energy is nothing but summation of H minus Ts. H is the enthalpy, S is the entropy. Now for the same conditions we are going to find out what is the partial Gibbs energy of A in this mixture, what is the partial Gibbs energy of B in the mixture, provided we know the enthalpy entropy values of pure components. I hope now you understand. Let us meet with the new lecture.